At the lowest level, your machine only understands one thing, ones and zeros. But humans don't think in binary. Python acts as a direct translator, letting you write instructions in syntax that closely resembles plain English, which the system then executes as machine code. In 1991, Guido van Rossum designed the language with a specific goal. Programming should be highly readable and accessible to anyone, not just computer scientists. When you first install the environment to write this code, there is one crucial step. You have to check the box that says Add Python to Path. Doing this links your terminal directly to the Python interpreter, allowing you to run your scripts from any folder on your operating system. By abstracting away complex, low-level machine instructions, developers could stop worrying about hardware communication and start focusing purely on logic. This readability is what allowed software development speeds to accelerate over the last 3 decades. When you start coding, it's easy to imagine variables as physical boxes where you safely store data. In reality, Python variables are more like sticky notes or tags. When you type a equals 5 and then b equals 5, Python creates a single integer object for the number 5 in its memory cache. Then it points both the a tag and the b tag to that exact same object. We can prove this by using Python's built-in id function to print the memory address of both variables. When we run it, the terminal outputs the exact same numeric string for both a and b. If you later reassign those variables to new numbers, the original 5 object is left without any tags pointing to it. Python detects this unreferenced object and automatically deletes it to free up space, a process called garbage collection. Understanding this labeling system is critical. If you treat variables as physical boxes, you will eventually modify complex data structures expecting only one variable to change, only to realize you've accidentally overwritten data across your entire program. This chart shows the syntax for Python's 4 core data structures. Lists use square brackets, tuples use parentheses, sets use curly braces, and dictionaries use curly braces with key value pairs. If we look closely at a list, it operates on zero-based indexing. In the string Telugu, the letter T sits at index 0, and the final O sits at index 6. You extract specific data by calling its exact numerical position. But if you need the final 4 letters and the list is thousands of items long, counting from 0 isn't efficient. Instead, you can count backward. Python allows negative indexing, where the final element is simply -1, the second to last is -2, and so on. These structures also differ in mutability. A list is mutable. You can append, remove, or swap elements after it's created. A tuple is immutable. Once you define its sequence, it is permanently locked in memory and cannot be altered. Choosing the correct structure depends entirely on how you need to handle the data. Using a mutable list for records that must remain constant, or ignoring the unique constraints of a set, creates logical vulnerabilities that break your program as its complexity grows. As programs grow, you'll often find yourself needing to execute the exact same 20 lines of logic in multiple places. Copying and pasting that block makes a script bloated and impossible to debug effectively. To fix this, you define a function using the def keyword. This wraps that complex block of logic into a single named entity. Now you execute all 20 lines just by typing the function's name. You also don't have to write every function from scratch. Python includes built-in modules. By typing import math, you gain immediate access to pre-written, highly optimized functions like math.squareroot without having to code the complex math yourself. By encapsulating logic into reusable functions and importing established modules, massive codebases remain readable. You fix a bug in one function, and that fix instantly propagates everywhere the function is called. Functional programming handles actions well, but the real world is built of objects. An application tracking inventory needs to represent actual laptops, phones, and accessories, complete with their individual properties and behaviors. Object-oriented programming solves this. You write a class called computer, which acts as a master blueprint. From that single blueprint, you can instantiate individual objects, assigning them to variables like comp1, giving them specific processors and memory capacities. Inside the class blueprint, you need a way to assign those specific details to the exact object being created. That is the job of the self keyword in the initialization method. When comp1 is created, it is passed into the method as self, ensuring the 16 gigabytes of RAM is attached to that specific computer, not every computer in the system. This means you can build a digital architecture that mirrors physical boundaries. By binding unique data and behaviors into distinct objects, you can scale a system to track millions of unique users or products without their data colliding. As you scale, you'll want your program to run faster by executing tasks simultaneously. However, Python uses a global interpreter lock, or GIL. This lock ensures that even if you spawn multiple threads, only one thread executes Python bytecode at a time, meaning threads alternate rapidly rather than running in true parallel. This is the architecture of Python. You use basic syntax to assign variables to objects in memory, group that data into mutable or immutable structures, wrap repetitive logic into functions, and finally, model complex systems using object-oriented blueprints. Mastering these interconnected mechanisms marks the shift from basic scripting to software design. This foundation allows you to architect digital environments that are predictable, modular, and built to handle real-world complexity.